Chapter 6, Introduction to Continuous Probability Distributions. In this video, we'll be learning about the exponential probability distribution. In section 6.2, there are two other continuous probability distributions in the textbook: the uniform probability distribution and the exponential probability distribution. While we're not learning how to do the uniform probability distribution, it is useful to know what it is and where you might see it. The uniform probability distribution is used when we don't have very much information, and so we can assume that the probability of any interval or range of continuous random variables is the same for any other interval or range of the same width. In other words, we assume all the variables have the same chance of occurring. So for the exponential probability distribution, which we will focus on, this is used to measure the time that elapses between two occurrences of an event. So for instance, we might want to know the time between hits on a web page, or the time between arrivals of customers at a bank drive-in teller window, or the time between failures of an electronic component. All of these can impact business decision making. Like, is our web page getting enough hits frequently enough? Do we have enough tellers for all the arrivals of customers to the window? And is the time in between failures a long time or a short time, and something needs to be fixed in a particular component? So the exponential density function, as you see here, takes our continuous random variable that's exponentially distributed, and we have our statement of f of x equals, and here's some Greek letters, our lambda times e, which is our natural log, minus lambda times x. And this assumes that x is greater or equal to 0, because you can't have negative time, right? So x is always going to be 0 or more. Note that the standard deviation of any exponential distribution is the same as its mean. Fortunately, we don't have to worry about this formula, but I just wanted to introduce it to you so that you are aware it exists. One more thing to note is that 1 over lambda is the mean time between events. This is really important to remember because you're going to need it when we're working in Excel. So for our exponential probability, this is the probability that a value will fall within an interval, is the area under the graph between 2 points of that particular interval. So this formula is useful because we can actually find the exponential probability with a simple calculator. And so this is the probability that our x is between 0 and some value of interest, say between 0 and 10 minutes, or 0 and 3 hours. The formula then is 1 minus e, our natural log, raised to the power of negative lambda times our a, or our value of interest. So what does the exponential distribution look like? I like to describe it kind of like a ramp where it's higher on this end and then it drops down going low. And so depending where your mean is, which in turn impacts your lambda, because your mean is the same as saying 1 over lambda, that will tell us the height and the shape of our exponential distribution. Excel gives us the cumulative probability from left to right. You're going to hear this over and over. For all our distributions, Excel is pretty consistent. Whenever we use our Excel functions to find a probability distribution, it reads from left to right. So let's look at an example. Problem 37 in the textbook. The time between phone calls to a cable television call center follows an exponential distribution with a mean of 1.5 minutes. So here's my formula. Part A asks, what is the probability that the time between the next two calls will be 45 seconds or less? So first we have to figure out what is our lambda. So our lambda is equal to 1 divided by the mean. And so we're going to take 1 divided by 1.5 minutes, and that gives me a lambda of 0.6667. Lambda and the mean are inversely related to each other. Note that in the first part of the problem, it described time in minutes. In our question of part A, it talks about time in terms of seconds. So we need to make sure to convert our time so that we are working consistently with the same units of measure. So 45 seconds or less is the same as saying 0.75 minutes. And I get that by taking 45 seconds divided by 60, because I know that there are 60 seconds in a minute. So that means our A, our event of interest, that's this part right here, is 0.75. Then what we can do using our calculator to find the probability that my x is less than or equal to 0.75 minutes, we will take our formula right here, 1 minus our natural log raised to the negative lambda that we found over here, times our A, our value of interest. So what I like to do in my calculator is solve the exponents first to make sure I enter it in correctly. And so that's the same as saying 1 minus e to the negative 0.5 when I multiply lambda and a. I don't want to forget that negative either. So see right there in the formula. And then using my calculator, when I take e to the negative 0.5, I get 0.6065. Then I'll subtract that from 1. And so the probability that the time between the next two calls will be 45 seconds or less is 0.3935 or 39.35%. Now, how do we do this in Excel? Using the same scenario, we can use the formula builder by clicking on the Formulas tab, Insert Function, Statistical Category, and select Exponential Distribution. You'll enter your x and you'll enter your lambda and type in true. Note though that you'd have to still do the hand calculations to figure out what our x was, the 0.75, which is the 45 seconds converted into minutes, our lambda of 0.6667, which was found by taking 1 divided by our mean of 1.5 minutes. And then it's true because it's going to read all the probabilities from left to right. Let's do part B. Same scenario. We've got our call center with an exponential distribution with a mean of 1.5 minutes. Note though, in part B, we're asking what's the probability that the time between the next two calls will be greater than 112.5 seconds. So what I've done is I've simplified our formula here. So when we're looking for x is greater than some value of interest, in this case, the 112.5 seconds, our formula now is e to the negative lambda a. So again, our lambda was found by taking 1 divided by our mean, so 1 over 1.5 minutes, so that's 0.667. That hasn't changed, right? Same story, same mean. Still got to find the lambda. But we do want to convert our time in seconds into minutes. So we'll take 112.5 divided by 60, because I know that there are 60 seconds in a minute, and that changes our time into 1.875 minutes for our value of interest, our A. So the probability that x is going to be greater or equal to 1.875 minutes is I'm going to take this formula E, plug in my lambda, plug in my A, simplify it to make sure I get my exponents set up correctly to e at the negative 1.25. And when I use my calculator, I'll get 0.2865 or 28.65% chance that the time between the next two calls is greater than 112.5 seconds. For this scenario, again, we're setting up the probability by converting 112.5 seconds into minutes of 1.875. So here's my 1.875. And using my Excel, I plug in my 1.875 for my x, my 0.6667 for my lambda. I'll type in true for the cumulative, and then click OK. So here's our probability at 0.7135. So note though, our exponential distribution gives us the cumulative probability from left to right. That means it's this area right here is 0.7135. I don't want this area. I want greater than 1.875. I want this area right here. So to get this area, I'm going to do 1 minus 0.7135, which means the probability of getting greater than 112.5 seconds is 0.2865, which is this area right here. So you can see if you use the calculator, you can use the formulas on the previous slides, or if you use Excel, you have to be aware of are we doing greater than some number or less than some number. And if we're doing greater, we have to use the complement rule where we're going to do 1 minus the area over here in order to get this area that we actually want. So be aware of how Excel works and how the formulas using your calculator works. So in other words, we've covered in Chapter 5 the binomial distribution and the Poisson distribution. We did not study the hypergeometric, and these are all random variables based on counting. And then in this chapter, chapter 6, we learned about the normal distribution and the exponential distribution and how to use them. And we touched on the existence of the uniform distribution. And these are used when our random variables are uncountable and are determined by measuring. So if you have any questions, just let me know.